All right, welcome to the snow day video. It's kind of a quick recap of what we did last time. So last time we did the position vector, which again is the vector which points from the origin here to the location of an object along some trajectory, where the blue line here is the trajectory at any different moment of time. And then from there, we define the displacement as delta R is equal to the final position, which in this case is R1, minus then the initial position, which is R0, which again, this is just the slope of the line that connects the 2 points together. So in this case, this is my displacement. So this is my delta R. Uh, in Cartesian coordinates, this guy then splits up then into the displacement in the x direction, I hat, meaning the x direction, plus the displacement in the y, j hat. So this is the vector sum of the two. So basically all that means then again is this is my initial x position. This then is my final x position. Then my displacement in the x is simply this guy here. So this is delta x, where this is going to point in this direction. So this is my delta x. And then in the y direction, let me drop my line over here. So this is my final y position. This then is my initial y position. So that in this case, again, my displacement in y direction is simply this. So this is my delta y, which in this case is going to point downward in this direction. So that's my delta y as a vector, which in this case is in the negative y direction. So that's then my displacement. Our velocity that we came up with. So let's talk about our velocity. So our velocity. So the average velocity is simply equal to, so let's write this down. The V average is then equal to the displacement divided by the change in time. So this then is my average velocity, or in Cartesian coordinates, this guy then is going to be my displacement in the x direction divided by the change in time. Plus then my displacement in the y direction divided by the change in time, which is simply the same thing then as the average velocity in the x direction, I hat, plus then the average velocity in the y direction, j hat. Now, again, if this was in 3 dimensions, I would get plus a delta z in divided by change in time. So that is my displacement in the z direction, k hat. And then in this case, this would then be the average velocity in the z direction, k hat. So graphically, this is something I did not show last time. Let's kind of talk about that then. So again, all this statement here says is that what? Since the change in time is always positive, then the average velocity always points in exactly the same direction as my displacement vector, which in this case means that my average velocity then points in this direction. So that's my average velocity. From there, we can do our instantaneous velocity. So my instantaneous velocity v is simply equal to the limit delta t goes to 0 of then the average velocity, which in this case then is just going to be equal to the time rate of change, or the derivative with respect to time of the position vector. And then in Cartesian coordinates, this is also the same thing then as my instantaneous velocity in the x direction, I hat, plus my instantaneous velocity in the y direction, j hat. And then if I also have a z direction, this is then plus my instantaneous velocity in the z direction and in the x hat direction. Good. So this is my instantaneous velocity. So instantaneous velocity in this case, let's go back to our picture. Let's choose another color here. Let's do the blue color. That looks pretty. So in this case, it's just going to be the slope of the tangent line at that point. So in this case, this is going to be my initial velocity. And then my final velocity then would point in this direction. So this is then going to be my final velocity at this point. So it's just the slope of the tangent line at those two different positions. So cool. So those are then my displacements, my velocity, both average and instantaneous. So next thing we have, if our velocity changes with time, of course, that gives us the acceleration. So let's talk about our acceleration. So again, let's look at the average acceleration. So my average acceleration, A average, is then going to be equal to my change in velocity divided by my change in time, which is the same thing then as what my final velocity, let's call that v1, minus then my initial velocity, where divided by my change in time. These two guys are, of course, my instantaneous velocities at those points. Instantaneous. So that's my instantaneous acceleration. So in this case, again, we know that what? Delta t, in this case, again, is positive, which means that the average acceleration is going to point in the direction of my change in velocity. So what does that mean? So let's go back to our picture. So in this case, my initial velocity is kind of pointing down in that direction, and my final velocity is pointing that way. So let's put those two basically on top of each other and see what we get in this case. So in this case, my initial velocity points this way. My final velocity pointed this way, which means that my change in velocity points this way. So this then is my delta v, which means that what? My acceleration then points in that same direction. So this is then going to be my average acceleration. Right? So basically we just move those two vectors on top of each other, and then that is going to be my average acceleration in this case. So cool. So in this case, following the same logic, we can find then is that what? My average acceleration is the same thing as the average acceleration in the x direction I hat in Cartesian coordinates, plus then my average acceleration in the y hat direction, or the y portion of the average. And then again, if we have 3 dimensions, this becomes plus my average acceleration in the z direction k hat. So this is our average acceleration. So again, this is just the acceleration in my x direction. So again, if this is my x direction, so let's put this in the coordinate system. So here's my x and y axes. Then in the x portion here, I would have just a little tiny bit. So it's going to be what? This amount here. So this is my average acceleration in the x direction. And then in the y direction would just be this amount here. So this is my average acceleration in the y direction. And so it's just each one independently, just vector sum together. Of course, we have our instantaneous. Let's go to our instantaneous. Let's use this color here. So instantaneous. So my instantaneous, just like the velocity, is equal to the limit as delta t goes to 0 of my average acceleration. So that, of course, is just going to be equal to the time rate of change of the velocity. So my first derivative of the velocity. But of course, since the velocity is equal to the first time rate of change of the position vector, so this is going to be the second derivative of the position. Write that a little bit more clearly. There we go, divided by my change in time, or the second derivative. Component form, of course, this guy's just going to be equal to my instantaneous acceleration in the x direction, plus my instantaneous acceleration in the y direction. And again, if I have a 3-dimensional coordinate system, then I'm going to add on my instantaneous acceleration in the z direction. So that's it. Nice and easy. Life is great. So again, all that, the position, the displacement, the acceleration, and the velocity, all boil down to what is it doing in its own independent direction, vector sum together to give me the entirety of the vector itself. So let's do this. Let's do an example. Let's do my example here. Let me stop showing myself here. Good. So let's share my screen here. So let's share my desktop. Cool. So let's do an example of this guy. So let's look at this guy. So this says then that the instantaneous velocity of a particle moving in the xy plane is given by the following there. So I got that expression. So v is equal to 6t minus 4t squared I hat direction. So my x direction is changing with time, plus 8 in the y hat direction, where that's just simply a constant. So I want to know, what is the instantaneous acceleration at 3 seconds? When, if ever, is the instantaneous acceleration equal to 0? And then when, if ever, is the velocity 0? And when, if ever, does the speed equal 10 meters per second? So good. So let me stop sharing that screen. Let me bring up this screen again. Cool. All righty. So let's work on this. My computer yelled at. Okay, let's see here. Okay, so what we're told is, again, let's go back to our problem. Our velocity is given by, so this is 6 times t minus 4t squared in the I hat direction plus 8j. This is all going to have units of meters per second. Okay. So first things first, we want our instantaneous acceleration. So this is my time rate of change of the velocity. So this guy is going to be equal then to the time rate of change of the x component of the velocity, or the instantaneous in the x direction I has, plus then the time rate of change of the y portion of the instantaneous velocity j has. So looking at this guy, this is then going to be the time rate of change of 6 minus 4t squared in the I hat, plus the time rate of change of 8 in the j hat direction. So first things first, let's deal with the j direction. Of course, the time rate of change of a constant is simply 0. Constants don't change with time, so that term is 0. And I just realized here I forgot my t, so let's put in the t there. So it's actually 6t minus 4t squared. There we go. For this guy, we can separate it into two different derivatives. So it's going to be 6 times the derivative of t with respect to t, which of course is 1, minus then 4 times the derivative of t squared with respect to t, which is then going to be a 2. So I get a 2 times 4, which is 8 times t, all in the I hat direction. So this is my instantaneous acceleration at any moment of time. So for part A, we simply want to know what is our instantaneous acceleration at 3 seconds. So this is my instantaneous acceleration evaluated at v, or t is equal to t3, which I'm just calling 3 seconds. So plug that in. So this becomes 6 minus 8 times 3 in the I hat direction. This is going to have units of meters per second squared. Let's see. So 6 minus 8 times 3 is the same thing as minus 18 in the I hat direction, meters per second. So this means that it's moving in the negative x direction at a speed of 18 meters per second squared. So that's the acceleration at that point. B says if, or when, and if is the acceleration equal to 0. Now, let's talk about that for a second. So this is actually the 0 vector. So a 0 vector means that all components of the vector are simply equal to 0. So in 3 dimensions, what that means then is that the x component is 0, the y component is 0, and the z component is also 0. Now, of course, here we have no z anyway, so we just don't care about that. Now, from the previous slide, what that means is we have our acceleration is equal to what? 6 minus 8t squared in the I hat direction plus 0j. So for this to be 0, we have to require that this first term here is equal to 0. So what that means is we need a 6 minus 8t, that's a t, not t squared, must be equal to 0, which means that t then, whoa, what happened? Hit a wrong button. There we go. So we have to have that t then is equal to simply what? 6 over 8, which is the same thing as 3/4 of a second. So the time of 3/4 seconds is the time when my acceleration is instantaneously equal to 0. Good. So part C then simply says that if and when is the velocity equal to 0. Again, my 0 vector. So again, what that means is that I have to have my velocity equal to 0 at all components. So I have to have that the x component, the y component, and the z component must all be equal to 0. Well, let's go back to our velocity. So that was equal then to, what was that? 6 times t minus 4 times t squared in the I hat direction, plus 8 in the j direction. Now, of course, the first term here we can set to 0, so that's possible. But since the y portion is equal to 8, we can never set 8 equal to 0 because it's always just a constant of 8, which means that the time that this thing is equal to 0 will be never. So this is never, not possible. And again, the reason for that is because the y component is 8 for all times, which means it's never going to be equal to 0, which means we'll never have a 0 velocity. So there's no way that this thing is possible. So cool. So next up, we have, what is this, part D. So part D wants to know, when can we have the speed equal to 10 meters per second? Now, for multidimensional vectors, what that means then is that the speed is equal to the magnitude of the velocity. Okay, and we want this guy equal to 10 meters per second. So the magnitude, of course, is by Pythagoras' theorem. This is going to be the x component of the instantaneous velocity squared plus the y component of the instantaneous velocity squared, square rooted, must then again be equal to, in this case, 10 meters per second. Now, using our original vector, this is going to be the same thing as 6t minus 4t squared squared plus 8 squared square rooted must then be equal to 10. I'm going to drop the meters per second for now. So in this case, we have to find what is the time t for this to occur. So we want to solve this then for the time. So first things first is to get the time, we have to isolate that first term under the square roots, which means we want to get rid of the square roots. So we're just going to simply square both sides at this stage. So in this case, I'm going to get a 6t minus a 4t squared squared must then be equal to 10 squared minus 8 squared. Well, 10 squared minus 8 squared is the same thing as 100 minus 64, which is the same thing as 36, which is then equal to what? Plus or minus 6 squared. Mm-hmm. So that'll be important here in just a second. So using this, what we can do then is now to get rid of the square here, we're going to take a square root of both sides. So let's take a square root of both sides. So I'm going to get a 6t minus 4t squared is then equal to the square root of plus or minus 6 squared, which is the same thing as plus or minus 6. Okay. Now, it's necessary, as we'll see here in a second, to keep the plus or minus. Now, let's go to here. So what we want is the time. So let's rearrange things to find time. So basically, I'm going to take these two terms and bring them to the other side. So finally, what I'm going to get is 0 then is equal to a 4t squared minus 6t plus or minus 6. Now, to find the t, we have to use the quadratic expression. So in this case, we know a is equal to 4. B is equal to minus 6, and then C is going to be equal to plus or minus 6. So let's plug those in. So this tells me that T is equal to minus B, which is 6, plus or minus the square root of 6 squared minus 4 times A, which is 4, times C, which is plus or minus 6, all then divided by 2 times A, which is 8. Okay. Now, let's look at this here. So first of all, if I keep the positive sign, so let's say I keep the positive sign in this case, or the negative sign. So let's look at this guy. So first of all, if I keep, for example, the positive sign, what happens in that case? So in that case, if I keep the positive sign, so in this case, let's say we keep the positive sign, under the square roots, we're going to have a square root of 36 minus 4 times 4, which is 16, times 6, which is the same thing as the square root of what? 36 minus something which is bigger than that guy. So it's going to give me a 36. So 36, so it's going to give me what? A 96, right? So in this case, this entire term then would be negative. So I'm going to have the square root of a negative number. Now, the square root of a negative number, of course, is an imaginary number. So this is actually going to be the same thing as an imaginary number times square root of that number. Now, time can't be imaginary, which means we can't have the positive term because the positive term is going to give me an imaginary number. So we have to get rid of that positive term. Now, if I keep the negative term then is going to give me a positive on the inside. In this case, I'm going to get a positive, which means everything will be real on the inside. So let's do that. So let's keep then the positive number. So in this case, this guy's going to be equal to simply 6 plus or minus the square root of those two numbers added together, which gives me 132, divided then by 8. This says units of seconds. Put all this in my calculator. What I find is this works out to be 2.19 seconds. So the time at which the velocity, in this case, or the speed will be equal to 10 meters per second is going to be 2.19 seconds. And again, in this case, we had to keep the -6 in this case, because again, the positive gave me an imaginary number. So we had to keep then the positive in this case. So good. So let's do another one. So this one, I'm not going to show you this slide. I'm just going to write it down. So this says that we have a proton, which is initially at some velocity. So let's call that V initial is equal to 4I hat minus 2J hat plus 3K hat. And then 4 seconds later, we have V4, which is the velocity at 4 seconds, is then equal to minus 2I minus 2J plus 5K hat. And of course, both of these two velocities are in meters per second. So in this case, wants to know over that time range of delta t equal to 4 seconds, it wants to know what is the average acceleration that this guy feels. What is my average acceleration in unit vector notation? So what do we know? We know for part A here, my average acceleration is simply equal to my change in velocity divided by my change in time, which is going to be the same thing then as what? My final velocity v4 minus my initial velocity v0, all then divided by my change in time. So this will be the same thing then as in component form. So I'm going to get a -2 minus 4. So this is my, actually, let me do it longhand. Let's do it that way. So component form, this is going to be the x portion of the final velocity minus the initial x portion of the velocity, I hat, all divided by my change in time, plus my final y portion minus my initial y portion, all divided by my change in time in the j hat direction, and then plus my final z portion minus my initial z portion, divided by my change in time in the k hat direction. So good. So from here, my final y portion is -2. My initial is 4. So let's plug that in. So I'm going to get a -2 minus 4 over 4 in the I hat direction. Plus, in this case, my final y is also -2 minus a -2 over 4 in the j hat direction. Plus, my final is 5 minus 3 divided by 4 in the k hat direction. Okay, oops, I erased part of it, that's okay. So I get a -2 minus 4, which is the same thing as -6 divided by 4. So -6 divided by 4 in the I hat direction. Here I get a -2 minus a -2, which is the same thing as -2 plus 2, which is then 0 in the j hat direction, plus 2 over 4 in the k hat direction. Now, this first term, of course, is the same thing as 3/2. So finally, I can rewrite this then as what? 3/2 and 4/2. So let's pull out the 1/2. So we're going to get a -3 in the I hat direction plus k hat meters per second. So good. So this then is my average acceleration. Good. So part B then wants to know, what is the magnitude of this guy? So part B then says, what is my magnitude of my average acceleration? So this guy by Pythagorean theorem is going to be the square root then of the x component squared plus the, this is of the average, so average x squared plus average y squared plus average z squared. So this guy then is going to be, so here I'm going to get a -3/2 squared plus 0 squared plus 1/2 squared square rooted. So that's going to be the same thing then as what? -3. So this is going to be a 9/4 plus 1/4 square rooted, which is the same thing as the square root of 10 fourths, which is the same thing as the square root of 5 halves in the units of meters per second squared. Now we want to know the angle. So C, so theta, A average, is then going to be equal to the inverse tangent of. Now, in this case, since it's only acting in the xy, or sorry, the xz plane, since there's no y portion, so in this case, we can say that our opposite side is equal to the z portion. So it's going to be A average z divided by my adjacent side, which is going to be A average x. Okay. So in this case, all we're saying then is I'm calling this my x-axis, and then this is my z-axis, since there's no y portion, so I don't really have to worry too much about that. So cool. So plug this in. So my average in the the z direction was equal to simply 1/2, divided then by -3/2. So the halves are going to cancel. So it's going to be a -3. And of course, the -3 means that what? We're -3 in this direction, positive in this direction. Oh, sorry, the opposite. There we go. I wonder why that didn't make any sense. So I got -3 in this direction. There we go. And then I got 1 in this direction, right? By 1/2. So that means my total angle should be this direction here. So that means I'm going to be in the second quadrant. So this is my angle of A average. So, but in that case, what I find is that this works out to be 162 degrees. So this is the angle of my average acceleration. So this then is our definitions now of the position, the displacement, the velocity, both average and instantaneous, and then the acceleration, both average and instantaneous, in a multi-dimensional space. So one thing to note, let's write that down, is when we're looking in multi-dimensional space, so more than 1D, a negative sign is no longer sufficient, right? So in one direction, we can say something like delta x was equal to negative, I don't know, 3 meters. So that meant that what? This was my x-axis. So if this was my origin, then 3 was on this side, and then -3 would be on this side. So it just basically means we're pointing in this direction. But now, since I'm working in multi-dimensional space, I can't simply just say that my delta r is equal to, I don't know, -5. That doesn't make sense anymore because that's actually a magnitude. So in this case, we have to either put it into unit vector notation. So again, my delta r must then be equal to some number. So it's my delta r x in the I hat direction plus my delta r y in the j hat direction, or give the magnitude of delta r and then an angle of delta r. So in this case, let's write these as numbers. So in this case, putting simply a negative sign doesn't really tell me anything. So I have to have a magnitude and a direction, or I have to put it in unit vector notation to then designate what direction it's actually moving in. So good. So anytime I have more than 3D, I can't just simply put a positive or negative sign out there. So next thing we're going to look at is, so these things are great, but how do we actually solve problems? How do we actually solve a multi-dimensional problem? Multi-dimensional motion problem. So let's look at a couple things and see how we actually would solve each one of these. So let me switch over and share my desktop again. Desktop. All right, so let's watch a couple quick little videos here. So first one we're going to watch is actually this one. So this is, I actually stole it from MIT, as you can actually see on here. So Anyway, so this is what's known as a relative motion gun. So basically, a guy's going to come out here. He's going to load the gun, put basically a golf ball in there, and then he's going to push it. So right around here, I don't know if you guys can see my arrow here, but there's a trigger, which is going to cause a golf ball or whatever the ball is to go out of the gun, fly into the air, and then land back in the cup here. So basically, what I want you to watch is the following. So when he pushes it, I want you to watch how this thing only moves in the Y direction. And then that's going to be the first time I run it through. The second time, I want you to watch how it moves in the X direction. All right, what happens to the ball's motion in the X direction? And then finally, the overall trajectory that this thing actually makes. So let's do that. So let's play this one. So again, here is the trigger. That's that little spike there. So good. All right, so that's the first time. I'm going to do it in slow motion. It's the trigger, bounces up, lands in. Okay, so let's back it up. So that was in the overall motion. So again, let's watch. So he pushes it. Notice that the ball in the Y direction goes up and then comes straight back down. So in the Y direction, it simply goes up and then comes down. So let's back it up. In the X direction, notice what happens is the ball follows the bucket. Okay. So in the X direction, it simply moves along with the bucket. Okay. And now let's watch the overall trajectory. So the overall trajectory then goes up, turns around, and then comes back down. So the overall motion is actually just a parabola. Now let's watch another one. So here, what's going to happen is a person's going to be driving in a car, and they're going to do it from the viewpoint of the car, and they're going to be holding a water balloon, and then they're going to drop the water balloon while they're driving. And let's see what happens in this case. There's the water balloon, they're accelerating, and then they're going to reach a constant speed, and then he's going to drop the water balloon. And notice what happens with the water balloon. It falls straight down. Okay. So it goes straight down directly under his hands. Okay. So what does that mean? So that means it's moving in the Y direction, but in the X direction, it's moving with exactly the same velocity at which the car is moving or what he dropped it. Now from here, it's going to show, hopefully, no, it's not going to do it. Okay, never mind. It would show it from the outside portion, and from the outside portion, again, it would look like some sort of parabola. Okay. So basically, this tells us some important information. Right? So the important information that this thing actually tells me is that the motion of an object in multiple dimensions is actually independently what it's doing in the X direction and what it's independently doing in the Y direction. Right? So basically, when I take my eraser, which as you guys know, I love to do in class, I throw this eraser, it's going to make a motion that looks something like this. Okay? Now, the overall motion of this can basically be broken down into two things. How it moves up in the Y direction, so my maximum Y direction here, good. And then how it moves back down. So it's moving independently in the Y direction. And then in the X direction, it's going to move from this location to this location. So it's then moving in the X direction as well. Now, I said independently, but it's not exactly independent. So this overall motion can be broken down into how it's moving in the Y direction. So how it moves in this direction. And then how it moves in the X direction. Now, but how it moves in the Y direction is not independent of how it moves in the X direction because something tells it when the eraser is at this horizontal direction of X, it has to be directly at this vertical portion of Y. So what is it that communicates to the Y portion what the X portion is doing and to the X portion what the Y portion is doing? What is it that tells it, hey, you have to be at this vertical height if I'm at this horizontal distance? Or that vice versa, you have to be at this X position if I'm at this vertical position here. Mm-hmm. So what connects the two of these guys together is simply the time. So what happens then is it moves in the y direction and it moves in the x direction. But what relates these two directions together is simply time. Okay. So what does this mean? So this means that when I'm looking at multidimensional motion, as this object is moving, we're going to look at simply the y direction, how it's moving in the y direction, which means we're going to write a kinematic equation for the y direction. We're going to look at how it moves in the x direction, and then we're going to write down a kinematic equation of how it moves in the x direction. And then what relates the x and the y together is the time. Now, which one do we solve for? Well, ultimately, we're going to solve for the time by using whichever one it is has the most amount of information in it. Okay. So now from here, before we start solving these and showing you how to actually solve these, let's make some assumptions. So what are going to be my assumptions for this? So assumption number one is that we're going to ignore air resistance. So what does that mean? So if I ignore air resistance, it means we're living in a vacuum, so we can't breathe and we're all dead, but that's okay. But we're going to ignore the air resistance. And what this means then is that what? If this is my usual coordinate system, x and y, that means that my acceleration in the x direction will be equal to 0, and my acceleration in the y direction will be equal to g. So in this case, we're going to have the acceleration due to gravity pointing straight downward. But as this guy moves, my acceleration in the y direction is g, but my acceleration in the x direction will simply be 0. So what does that mean? So that means that my velocity in my x direction will be equal to my initial velocity in the x direction, plus then my acceleration in the x direction times time. But since this guy is equal to 0, this then means that my final velocity in the x will always be equal to my initial velocity in the x. And I'll draw that in just a second here. Assumption number two. Assumption number two is that we're going to ignore the rotation of the Earth. So what does that mean? So we know that here's the Earth, kind of. This is my rotation axis, and we know the Earth is rotating about this axis, right? So what that means then is basically if I was sitting here, right, and let's say this is my US, okay, so here's the US, and I wanted to, I don't know, send a rocket to someplace over here, right? So let's say, I don't know, here's the place I want to send a rocket to, and I don't know, let's say, I don't know, what do I want? This is, I want to be somewhat politically correct over here, but let's say this is country Z. There we go. So basically, if I try to send a rocket over here and this thing is flying over this way, what's going to happen then is the Earth is going to rotate out of the way, which means the actual trajectory of the rocket is going to miss and hit something else. Right? Which means instead of hitting country A, we're going to hit, or sorry, country Z, we're going to hit then country Y. Right? So basically, this is what's known as the Coriolis effect. So the Earth rotating actually causes a force on this guy, which actually causes it to miss the trajectory, or the trajectory misses the target at which it is that it's trying to hit. So we're going to ignore that, which basically means that we're not going to fire from our country to some other country, but we're going to shoot over short distances so that the Earth really hasn't rotated the target out of the way. So this is our assumption number two. Those two assumptions together basically means that the motion of the object will follow a parabolic path. So these things mean that what? The motion will be parabolic. So good. So let's look at this. So basically, let's put all this down into words, okay? Or at least into pictures. So let's say here's my XY coordinate system. So as I shoot this object, here's initially my object. Let's say I give it some initial velocities. My initial velocity is going to be off in this direction, so v0. And I'm going to shoot this at some initial angle, say theta 0. So ultimately, my object is going to look something like this. It's going to follow this particular path here. So if I can draw close enough. There we go. Actually, that's a little too curved there. So let's do there. Okay, looks great. So From our previous slide, we know that the velocity at any position will be equal to the initial velocity. So that means whether I'm looking here, 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 or here, the velocity in the x direction will always be exactly the same. So always the same magnitude pointing in exactly the same direction. So my velocity at any one of these points will be equal to the initial velocity at all of these different points. Now, the y portion of the velocity, though, the y will be equal to the initial velocity in the y direction minus g times t, because in this case, I'm taking that what? The positive y direction is upward, g is downward, so that's going to make it a negative, which means as the object is moving, it's going to slow down, right? So basically meaning that initially, my initial portion of my y velocity, at least at this point, would be what? This high, right? So this is my initial y velocity. At this point, it's going to shrink down, going to shrink even smaller here until it reaches this point here where the y portion of the velocity will be equal to zero. So at its apex, it's going to have zero velocity. And then as it starts going down, where the velocity then in the y direction will grow vy. Now, as we did as a group assignment in class, what we know is by the time it gets back to the original starting point, the final velocity will be equal to minus the initial velocity in the y direction. But just notice that's what at every single portion, the size of the y velocity is changing because of the acceleration due to gravity. However, the x portion is not changing. It stays exactly the same. And that's because there's no acceleration in the x direction. So again, ultimately, my motion then is going to be parabolic. We're going to have no acceleration in the x direction, which means that it stays exactly the same velocity. But we do have a velocity in the y direction. So basically, all we're going to do now is start kind of working on some problems and see how we actually solve these things. So most of the time, let's say like 95% of the time, what we're going to work with are the second kinematic equation. And the reason for that is that most of the time we're going to know some distances and some heights and things like that, and we're going to have to find what it is that we're looking for. So let's look at a first example here. So my first example says that what? Here's my waterfall. So here's the waterfall. So my waterfall is some height. So let's say this is my height of 50 meters. And let's say my water starts off on the top. So here's a droplet of water, which is going to be moving in the horizontal direction in this direction with some initial velocity. Let's call that the initial, which is equal to 2.7 meters per second. Now, once the water comes off the top, it's going to undergo parabolic motion, something like this, and then it's going to hit some distance d away from the base of the waterfall. Okay? What we want to know in this case then is simply what is d. All right. So basically, let's start off with what I said. So here, since I know the height, I know the initial velocity, I know that the acceleration due to gravity is downward, and we're looking for a distance, we're going to use our second kinematic equations. Okay. So I'm going to write one for the x direction. Let me do that over here. So I'm going to write down my x direction, and we're also going to write down our y direction. Now, since we're working for the second kinematic equation, this becomes x is equal to x naught plus v naught x times t plus 1/2 the acceleration in the x direction squared. And this is going to become y then is equal to y naught plus v naught y times t plus 1/2 g, or sorry, 1/2 ay t squared. Now, first off, we already know this guy has no acceleration in this direction, in the x direction, so let's get rid of that. Now, because we're working with vectors again, as we talked about when it came to one-dimensional motion, we have to choose a coordinate system. Now, again, my coordinate system is non-unique. I can do whatever it is that I want. And in this case, I'm going to show you that by choosing this coordinate system here. So let's say that's what? This is my y direction, which means that this is going to be my x direction. So we're going to take it pointing downward, just for funsies. Right? So now let's use our coordinate system to basically start getting rid of some stuff. So according to my coordinate system, the initial position of my water droplet here is directly at the origin, which means the x component is going to be 0. So my x initial will be 0. My y initial will be all of the, or sorry, my initial velocity will, in the x direction, will be all of the velocity because it's moving horizontally off the top. So this becomes now v0 times t. Okay. Now, let's back up for just a second. So what this thing says is I can find the distance d here if I know the time. Now, at this point, I don't know the time. So I have to find the time. Where's the time going to come from? Well, it's actually going to come from this equation here. So from the y. So let's use our coordinate system and start getting rid of some stuff in the y direction. So from the y direction, what we know is that, again, the initial position of my water droplet here is at the origin. So my y portion is going to be 0. My initial velocity is 0 since it all points in the x direction. And my acceleration due to gravity will be a positive g because it's pointing in the same direction as my positive g. So in this case, I'm going to get a y then is equal to simply 1/2 gt squared. Now, typically the way this works is after we've used our coordinate system, we are going to find the time from the direction where we have the most amount of information. And in this case, as I just said, our most amount of information is actually the y information because what we know is by the time the water droplet falls the total distance of h, we call that simply h in this case, the 50 meters, the water droplet has simultaneously moved the total distance of d. Right? So all this means then is by the time this thing reaches the bottom of the waterfall, y then must be equal to h. So in this case, I'm going to get an h then is equal to 1/2 gt squared, which means t then must then be equal to the square root of 2 times h over g. Okay. So this is the time at which the water droplet has fallen the total amount of 50 meters. But this time here is exactly the same time as it takes for this thing to move the total distance of d. Okay, so basically to find d, all we're going to do then is evaluate this thing here at the time of the square root of 2h over g, which is the same thing as the square root of 2h v0 squared over g. So let's put our numbers. So this is then going to be 2 times 50 times 2.7 squared, all divided by 9.8 square rooted. So this works out to be 8.6 meters. So the total horizontal distance that this thing travels is 8.6 meters. So I only got about 2 minutes left. So I guess I'm going to stop here and basically say that's what. So next time, we'll start off with a more complicated one where we're going to have initial velocities in both the y and x direction, and then basically do exactly the same thing. And then we'll look at another problem and then talk about some stuff and then kind of go from there. So, all right, so that's the end of this video. As always, let me know if you have any questions. We'll pick up from here next time, whether that is at the university or not, and pretty much go from there.